The parallel axes theorem tells us this. We've studied the moment of inertia of a solid body, and we can calculate that by saying the little incremental moment of inertia of some little incremental amount of mass is dm times r squared, and then integrating that over the whole body. And so we've been able to find the moment of inertia of many different objects, and that's all in a table in your text. The question is this: if instead of rotating about the center of mass, what if we're rotating about some other point? How do we find the moment of inertia then? We could simply just integrate over that whole body again, as we did initially, to get the moment of inertia of the body itself about its center of mass. We could do that if we love calculus and we want to integrate. However, we could also take a look at the body and recognize this motion is the sum of this motion plus this motion. So as we rotate around in a circle, the center of mass is doing this, while the body is rotating about the center of mass. And so if we put those together, we have this motion. And we can show then that the moment of inertia of the body about this external center of rotation, or some other center of rotation other than the center of mass, is just the moment of inertia of the body itself about the center of mass, plus the extra moment of inertia due to all this mass at this distance. We can show this by saying the kinetic energy of this rotating body can be thought of as a kinetic energy due to the rotation plus the rotation of the body itself about the center. And we just add those two. This is the kinetic energy due to the rotation about the center of mass. This is the kinetic energy due to the fact that the body itself is going around this center of rotation. We substitute in the velocity of this center is just omega times d, the distance from the center of mass we are rotating. We pull that d out and we recognize the body itself is rotating about its center of mass with the same omega that the body is rotating about this external center. And when we put our terms together, we find that the effective moment of inertia of this body rotating about some other point is equal to the expression that we define here above. And so, for instance, we show in the table in your book, and you can integrate it out if you like, that the moment of inertia of this book rotating about its center is equal to 1/12 its mass times the sum of the squares of the two dimensions. But what is the moment of inertia if we're rotating about this point on the corner? Well, we have to add this extra term. And substituting in r, we use Pythagorean's theorem, recognizing that we're in the middle of the object, so we need a over 2. We substitute this in, and we have 1/12 plus 3/12 is 4/12 or 1/3.